So this video is a continuation of another video I did in which I explained the derivation to find the initial flow rates and the change in height over time of two spherical tanks in which the two tanks are connected by a tube, and the second tank has a second tube in which the flow goes out of it. So this is the coding for that problem. So for this code, I've already went ahead and imported all the stuff we'll need for this. We'll use the solve-ivp, which is solving initial value problem later. We'll use plotly subplots, jax.numpy, all that stuff. So for this problem, it doesn't matter really what t-end is. I just chose 2000 because it's a large number and we'll get a better graph that way. This SQ2G is the square root of 2 times the acceleration of gravity, which is 2 times 9.81. We're going to have the radius of the first sphere as 4, the radius of second sphere as 2, and those are meters. The area of this A12 is the area of the tube connecting 1 and 2, so that will be 0.2 meters squared. This A2 is the area of the tube exiting 2, which is also 0.2 meters squared. And we are going to have the initial height of the water level in 1 as 5 meters, and the initial height of the water level in sphere 2 as 3 meters. So here we have some equations for the initial flow rates. Again, these were all derived in my other video, so I won't be explaining the work in this one. This is just purely based on coding. So what we're going to want to do at the end of this one is to print these. And I forgot to bracket around this one. So this is pretty much just for later. It does, and so here we can just see the initial flow rates, which will be used later as well. So next what we're going to do is we're going to create a model, and we are going to call it switch. And the variables we will need will be quite a few. We are going to need t, which is time, v1. This is not supposed to be v1. It's supposed to be v2. V1, velocity 1, velocity 2 is v2. The t switch, which is time for the switch, and then the scale for it. This will become very important when we create more models involving the Q1N and Q2N and all that stuff. And when we need to switch the percentages to the things listed in the problem. So we are going to have this return. We are going to have jax.mp, no, not mp, and this is from the import stuff at the very top. So we are going to have jax.nn, sigmoid function, t minus t switch in parentheses, and this will be divided by the scale times v2 minus v1 and plus v1. So I'm going to go back, and when I code, I like to space stuff out near operations such as adding, dividing, subtraction, multiplication. Just makes it easier to read and stuff. So we now have that model. So now we are going to define the models of Q1N and Q2N, and the switch will become very important for it. So we will start with Q1N, and it will be in relation to time. So what we'll return for this one is we will have this switch, which now if you look and we put the parenthesis right here, collaboratory, this programming software, is nice enough to recall what we need to have in the switch. So the first thing we need is time. The second thing is V1, so we will have Q1 and I. For the second thing, we are going to have 0.8 times Q1 and I. I need the 1. Then we will have the time of switch, which is 100, and the scale will have 0.001. So the reason why we did this 0.8 times Q1 and I, that is 80% of the initial flow, which is what we want for the problem. So now we will have another one for Q2N. It will also be in relation time, and it will return a similar thing, except we will have Q2 and I for here. And for this next part, we want 2.5 times Q2 and I. And we want to 200 and 0.001. So this 2.5 is 250% of the initial. So hit Shift Enter. Now we have all of our models for our variation height at a given time. So we are going to make yet another model. And as you can tell, this one is called DHDT. This was derived in my previous video, in which h is the height, so it's the difference in height at some difference in time. So what we'll need for this one is t and h, which is time and height. So we will have, what our end goal is to have an array of values. So what we will have is this h1 for the height of the sphere per sphere equals h of this 0 index number. This 0 index number is the first term in the arrays. So when it solves for Q1, it will put all the values and stuff in this first array for the first sphere. And similarly, we're going to have the second sphere, except its index is 1 because that's actually the second term. So now we want the value of Q12. Well, the value of Q12 is essentially the same as up here, with the exception none of it is I. I don't know why that didn't. There we go. So we are going to get rid of all the i's. And we also need it for Q2. And just like for the Q12, we are going to get rid of all of the i's because we no longer want the initial values. So now something else we want is the cross-sectional area. So we will find the cross-sectional area of the first sphere. So first we'll need pi, which the number pi. So here we do j and p dot pi. As you can see, it's 3.1415, whatever pi is. And then we are going to multiply that by the radius. We want R2, we want R1. So we're going to have the radius squared minus R1 minus H1. And this will all be squared. So that is the cross-sectional area of the first one. And the cross-sectional area of the second one will pretty much be the same, except all of the R1 and H1 values will be R2 and H2. So I'm going to go ahead and change those to what they are. And make sure you change the variable name or else it will pop up an error. So now we will return an array. So we'll have Q1n t minus Q12, and all of this divided by AC1. And we also want Q2n almost forgot to add in the parenthesis t. And we're going to have Q12 minus Q2, all this divided by cross-sectional area of 2. So we got these values because Q1n, so for the first sphere, Q1n is the only thing adding flow and liquid to the first sphere, and the tube leaving it between the two spheres is the only thing taking it out. So that's how we get this for the first sphere. And the second sphere has flow coming in, that's Q2n. And it also has flow coming from the tube connected between the two. But then the only thing leaving is the flow from the second tube. So now we have that. So now we want to solve the initial value problem. So we are going to have this variable res for resolution. We are going to call upon the solve IVP function, which I mentioned earlier. Our function is DHDT. The time span is from 0 to Tn. The heights is H1i to H2i. Our method we will use will be this. And dense output we will have be true. And for event, we'll have Jack equals Jack's dot Jacobian. DHDT. So now what we are going to do is we're going to call a variable tplot, do jmp.linspace. So where we want to start will be 0. We'll want to go to tn, and we'll do 501. So now we are going to have a variable called solution. Well, sol, short for solution, was what I meant to say. We're going to have this res.sol, and we're going to have it for tplot. Hit Shift Enter. So it pops up an error, says it's in the res line. It's probably, yes, here it is. So the error occurred because I did not have parentheses around these. So let's see if that works. All right. Oh, did I forget a period? I did. I forgot a period all the way up here. Now it's loading. Still loading. All right, it worked. So that just goes to show how syntax errors and things like that, simple forgetting periods and parentheses, can lead to errors in programming. So now we want to display our results in nice little graphs. So we will have a variable, we'll call it fig, short for figured. And we'll call upon the make subplots. And we'll have 1 row, 2 columns, which what this pretty much means is we'll have 2 separate graphs. They'll be on 1 row, right side by side to each other horizontally. So now what we want to do is add to this figure. So we'll do fig add. We'll have trace. And we want scatter plots. So we'll do, well, kind of scatter plots. They're technically scatter plots, but they'll eventually be a line plot. So we'll have go.scatter. We'll have the x-axis be tplot. Y equals solution for the first array, which is H1. So like if you remember up here, we have H1 equal to the first one. So now we'll have the name. We can just call H1. And we'll have rows equal 1, column equal to 1. So now we are going to add to it again, but we're going to have the solution be for H2 right here, and we're also going to name H2. So instead of retyping all of that, I'm just going to copy and paste, in which this is 1, name it H2, and we have all that. So now I'm just going to copy and paste to here, because we're going to be using it a couple more times. So now we are still going to have x equal to t plot, but now we're going to have y equal to the q1n, and we're going to have in relation t plot. And instead of the name being h1, we are going to have this called q1n. I forgot to put an apostrophe. And we're going to have this in row 1, column 2. And then I'm going to copy and paste this again. So now we are also going to do the same for Q2n and call this Q2n. So pretty much these first two, so these that are highlighted in blue, these are additions to the first plot, in which we are using the solution thing, and it's for the heights. But then these last two will be in the second graph on the right, because here we have them for row 1, column 2, which is the second graph on the right. So now if we hit Shift Enter, all right. Okay, yeah, that's what I did wrong. This call is, all of them are supposed to have an S for columns. So now if I hit Shift Enter, I'm not sure how to capitalize this S. No, that's not it. Rows. Okay, so for this, okay, so that's where I got this from. Okay, so for these trace ones, you don't add an S, which looking back makes sense because you're not going to really add it to multiple rows or columns at once. You just want a singular one. So now let's hit Shift Enter. I guess I do have to capitalize all these. Yep. All right. And here we have the graphs, which this is for the heights, and this is for the flow rates. So you can see this is H1, this is H2, and this is Q1N and Q2N.